In our everyday experience, the universe behaves like a giant, predictable machine. If you watch a baseball pitcher wind up and throw, you intuitively know the ball has an exact location in space and an exact speed. We can track those metrics without any logical contradiction. A high-speed camera can isolate the ball's position, and a radar gun can clock its momentum at that very same split second. But zoom in close enough, down to the atomic level, and that predictable reality. In 1927, a physicist named Werner Heisenberg realized that the quantum world refuses to play by these rules. He discovered that you cannot simultaneously know the exact position and the exact momentum of a quantum object. Pinpointing where a particle is automatically destroys your ability to know how fast it's moving, and vice versa. The natural reaction is to assume this is an engineering problem. It makes sense to think that our microscopes and sensors are simply too clumsy, bumping into tiny particles and messing up the readings. This limitation has nothing to do with our technology. It is a physical property of the universe, driven by the fact that everything exists as both a particle and a wave simultaneously. Look at the two absolute extremes of quantum behavior. First, imagine a pure particle. It exists at a single exact point in space. Because it occupies only that coordinate, it has zero oscillation. There is no ripple. In quantum mechanics, an object's wavelength dictates its momentum. So if you have absolute certainty about a particle's position, you have no wavelength to measure, which means you know nothing about its momentum. Now look at the opposite extreme, a pure wave. This is a uniform ripple spread evenly across space. It lacks a distinct location, but what it lacks in position, it makes up for in momentum. Because the wave is entirely uniform, we perfectly measure the distance between its peaks, its wavelength, giving certainty of its momentum. A real object in the universe has to actually exist somewhere, and it has to have some amount of speed. It cannot be an infinite wave, and it cannot be a motionless point. Reality forces a structural compromise. Physicists describe this necessary compromise with a concept called a wave packet. We built this mathematically by overlapping pure waves with slightly different wavelengths. When these waves interact, they cancel each other out in empty space and amplify each other in one central, localized area. This central bundle gives our object a roughly defined position. But to build it, we had to mix several different wavelengths together. We no longer have one clean measurement, so the object's momentum is now slightly blurred. The tighter you squeeze that position down for an exact location, the steeper the mathematical cost becomes. To compress that packet into a tiny point, you must inject dozens or even hundreds of different wavelengths. By successfully narrowing down the exact position, you've introduced so many conflicting wavelengths that the original momentum is now lost in the noise. Because all matter in the universe exhibits this wave-particle duality, absolutely everything is bound by this rule. No matter how sophisticated our radar guns or electron microscopes become, human engineering cannot bypass a mathematical law. This uncertainty is an inherent part of how particles exist. The object does not possess an exact position and an exact momentum simultaneously. Those two pieces of information cannot exist with infinite precision at the same time. The predictable behavior of our macroscopic world is an illusion that masks a bizarre, probabilistic quantum foundation. The Heisenberg uncertainty principle proves that nature refuses to be pinned down, leaving reality in a state of inescapable blur.